Cottrell
Cottrell, yeah.
will give us our next talk.
Right. So thank you very much for the invitation. It's an honor to be here. So today I'm going to talk about 3D gauge theories and gravity duals. So and this was based off of recent paper, Cottrell Hashimoto. And that is 1602, 765. And another paper, Cottrell Hashimoto and Hansen, which is 1509. 04749. And so the basic plan of my talk is first we're going to review n equals 4 3D theories. And then we'll talk a little bit about the gravity duals. And finally, I'm going to make some speculative comments about anti-branes. So first of all, why is this interesting? Well, a 3D n equals 4 theory has the same amount of SUSY as a 4D n equals 2 theory, and a lot is known about the 4D n equals 2 theories because there's cyber-width theory, and so we can say we have a very good understanding of those theories. So it's very tantalizing and very tempting to say we can understand these theories just as well. But it turns out to be a lot harder. You might say, oh, well, I can just dimensionally reduce and learn everything I need to know about these 3D theories. But it's not that easy for reasons I'll describe later. However, there is hope that we can have the same level of understanding eventually. Next, I'll talk about the gravity duals of these theories. So it turns out we can describe a certain class of these theories, well, at least give the best gravity dual possible within M theory, the lowest order level, two-dimensional level in M theory, and show where that breaks down and discuss what that breakdown means. And then we'll talk about anti-branes, and in particular, in 3D, anti-branes seem to be a little bit more manageable than they do in high-dimensional counterparts. And the reason this is interesting is because we live in four-dimensional theory with gravity, so the natural dual theory, the ADS-15, would be a three-dimensional theory. So if we wanted to learn about KPLC or things like that in the real universe, then we should first learn more about 3D gauge theories. So I'll discuss a little bit about that. First, review. So as a prototypical example, we can think of UN K flavors, and of course n equals 4. Now n equals 4 in 3D implies an SO4R symmetry, which we can break down into an SU2 Coulomb times an SU2 Higgs. So it turns out that the R symmetry has one component that only acts in the Higgs branch, one component that only acts in the Coulomb branch. So, and our multiplets will decompose as follows. So, and normally in n equals 2 language, we have a gauge field and a chiral superfield in our vector multiplet, but we go to 3D. this will decompose into an A vector, a 3 vector, and the third component of the vector, and then still we have a chiral superfield. So one reason that the level of complexity goes up when we go to 3 dimensions is that before, as we just saw in 4 dimensions, the moduli space is characterized by the expectation value of this chiral superfield. However, when we go to 3 dimensions, now we have a moduli space parameterized again by this, but also we have the third component of the gauge field, and we have a 3 vector which can be dualized into a scalar. So one more step, this becomes a scalar, dual photon, an A3, and still the complex scalar. So now we have 4 scalars. Those can all obtain vevs. So our Coulomb branch for U1 theory will be 4-dimensional. In general, will be 4n-dimensional. So it becomes at least twice as large, and a lot of the nice properties we had about holomorphy and whatnot are no longer immediately useful. In addition to this, when we compact, if we started with a 4D theory to compactify, we'll have new instantons formed by monopoles running around the compact circle. So things become more difficult. Okay, so the running of the couplings in this case. Yang-Mills coupling. So UV value, then plus k minus 2n, with 4 pi r, where r is the SU2 invariant formed by phi and A3. So it's some measure of where we are in the Coulomb branch. So based upon this, we can already make a classification into 3 kinds of theories. So good theories. And this is when k is greater than equal to 2n. So this is the terminology of Gauder-Witten. And for these theories, we see, of course, that the Yang-Mills coupling will go to 0. So we have an IR fixed point that's interacting, and it's a standard IR fixed point. So we have ugly theories. So for k equals 2n minus 1, and in this case, naively, this is going to diverge, but you can actually rewrite this as a product of a free theory and a gauge theory of lower rank. So the ugliness of it is that the IR theory is not a simple theory. It's a product of 2 theories. And then we have what are called bad theories. And that's just anything k less than 2n minus 1. And of course, then the coupling goes to infinity naively. Now, the reason these are, we would just call these asymptotically free if this were a 4D theory. Here, the terminology bad is meant to not indicate asymptotic freedom. It's meant to indicate the fact that there's some operators in this theory that tend to become free. And the evidence provided by Gauder-Witten is that you have some monopole operators called Y. Normally the dimension of an operator is related to its R charge, but it's a UV R charge. So RY, UV. Sorry, it should be the IR R charge. But that might not be the same as the UV R charge. And the problem occurs if this UV R charge is too small. So it drops below the unitarity bound. That's 1/2. And then if the theory is unitary, then we can't identify the UV and IR R charges, and we don't know what happens. but the natural conjecture is that these operators decouple, and we end up with a decoupled sector.
So what again was R in the top formula?
Oh, so it's basically, so I can form some, if this were, say, the moduli space is 4-dimensional, but I can form an SU2 invariant. So you could think of it as a circle fibered over some R3, and then it's just going to be roughly A3 squared plus 5 squared equals R. But I just wanted to leave it, I don't want to go into details yet, but it's some kind of scale of the Coulomb branch. It's some bevel of
Is
the
it
Coulomb
the
branch.
fact that the gamma takes values on the circle?
Yeah, the gamma takes values in the circle. So,
So it's like the radius.
yeah, so this is like, you could think of this in the simplest case as something like a tau nut space, and this is some radius in the, so it's a circle fibered over an R3, and this is the radius in R3. I could have given it, maybe that's not a good name, because it has dimensions of energy, so it's it's like, I could have written like this.
Yeah. So, and what does it mean when you're saying things like Gn mil squared is going to 0 for?
So,
in other words, it's dimensionful.
yes.
As is GUV. That right?
Yes.
That GUV squared is some scale
Yeah.
defined microscopically, right?
Uh-huh.
But that scale phi is
Mhm.
arbitrary, right? I mean, it goes to note they differ by different points on the moduli space.
So the scale phi, I'm thinking about proving this theory at the scale phi, or so let me draw a brain picture. Maybe that will.
But it seems irrelevant. I mean, no. It seems irrelevant that formula is the value of the denominator.
Sorry, what?
Why is it that if the denominator is like bigger
If
than
there is a minus, you can have a 0 the right hand side of integral g.
So
a minus 5, or the value of phi, the right hand side is 0.
oh, I see, because it's positive. I see.
yeah. So when k is greater than 2n, then it. Okay. So, well,
that's not the right word. They're all
not the right
super
word,
normalized.
they're not all S, but I'm curious, if you have large enough number of hypermultiplets, then the coupling can still go to 0.
What 0 and
Relevant
I don't
coupling.
understand what you mean by goes to 0.
I think it means maybe 5, when 5 goes to 0, if you go to infrared, then the
Yeah.
diameter goes to 0.
The dimension just come,
In the infrared.
Which is
which is I think made out of the angles and that scale.
Hmm.
Phi, yes.
Yeah, you could.
Is 5 fixed?
No, phi is
No,
phi is not
you
fixed.
mean
Phi is
it's
something.
more
Phi is a
like
probe. Like I'm thinking one particular. So I could imagine an SU in theory, and I pull off one U1 and I measure the theory of that one U1. And then this is the coupling of that one U1 will see if it's at a point phi on the Coulomb branch. Yeah, you could rephrase this in terms of dimensionless quantities, I guess. Just maybe multiply everything by phi.
So 5 is the amount?
Phi is the of. Look, let me draw a brain picture. Make this more clear. So I can engineer this theory. It has 5 brains, and I could have some D5 brains in the perpendicular direction, and these are D3 brains stretched between them, so n of them, and that's 5, D5, D3, 0, 1. Okay, so and this is 0, 1, 2, 3, 4, 5. So the NS5s are oriented this way, and then the D5s have to be parallel in 3, perpendicular in 3 to preserve SUSY, and then 0, 1, and then along the 6. Okay, so this formula basically, well, interpreted in language of branes means if these branes will do some bending, and the effective coupling, which is related to the length here, as measured by one of these branes or one particular U1 pulled off onto the Coulomb branch, will see this dependence on the coupling. I mean, I guess maybe what's confusing is that the Yang-Mills coupling is dimensionful in 3D, I don't know if that answered the question.
Yeah, I still, maybe I'm just missing something obvious. I still don't know what the meaning of saying that d squared Yang-Mills is going to 0, or even if it's being measured, if we can measure the same method ratio of d squared Yang-Mills over 5.
You don't need some values of compactification there. The PUV is 4D cup.
No, 3D. This is pure, this is all just a 3D system.
Yeah, you know, actually, I had this discussion with Aki, and I thought we should rephrase in terms of dimensionless things, but he's like, no, it's fine. But I agree with you. It should be ultimately, you could be comparing the dynamics of maybe 2 different branes, and then say I had a brain pull off here and a brain pull off there, and then I compared some kind of scattering amplitude on this one versus that one. I mean, you could try and rephrase it in terms of dimensionless things, and that would make more sense. I agree, but so it just means that relative to another brain, relative to some other point on the Coulomb branch, has this value. So
the difference though between k bigger than or less than 2n in the brain picture is just the direction that the brain's
the direction of bending.
Yes. And so in the ugly and bad theories, the brains bend and the NS5 brains would bend and intersect.
Yes, the ugly and bad theories, they tend to intersect. So yeah, let me draw that.
Sorry, this capital M, is that what is usually called large M? This is the M which goes to infinity?
The capital N?
Yes.
It's a
capital
number of flavors, right?
UN.
No, it's UN.
Oh, UN, okay.
Yeah.
It says will go to infinity or it will stay finite?
Well, eventually, in the gravity dual, will take it to infinity.
And in the gravity dual, I assume G-string goes to 0, right?
Yes.
So I assume that the statement GM squared goes to 0. Is that the result of taking the G-string to 0?
No. So,
I think that was a question of more about
yeah, no, so
what the IR behavior is, whether it is
G-squared
0 or
Yang-Mills.
large. Whether that,
this
see,
is
normally,
GS
if we take that
LS.
lower dimensional Yang-Mills, we measure it with respect to the volume in which the system is in. That's one way of doing it.
So,
Some IR scale.
yeah, so both of these go to 0, basically. So G-squared Yang-Mills is quote-unquote fixed, although I agree it's dimensionful, so it's subtle what it means to say fixed. You always need to introduce some other scale to say it's fixed with respect to that scale. But you could, if you wanted to, rephrase this in terms of ratios by asking more interesting questions. And so this is, yeah, there is more work to do there. Explicit. Okay. Okay, so again, the brain bending effects, they make some of this dynamics more clear. So naively, if I have brains, D3 brains stretched between 2 NS5 brains, you'd have a picture like this, but the bending makes them want to do this. So this is the naive picture, and with n equals 4 SUSY, actually this is one loop exact. There's no more perturbative corrections. So so this picture is correct up to instanton corrections. So So obviously something weird happens here, and to understand what happens, we need to know the structure of instant-time corrections, and it doesn't immediately follow from the Seiberg-Witten theory in 4D, because of new instantons emerging. So likewise, if I have D5 branes in between the 2 NS5s, they'll induce some kind of bending like this. And you can see from the Hernani-Witten transition rules that the cutoff at k equals 2n is very natural. So So if I have n branes, ND3 branes, or SUN, and I have, let's suppose I have n plus ND5 branes. Now the Hernani-Witten transition rules tell me that this theory will have the same IR theory whether or not I move these branes past the NS5 branes, provided I account for the Hernani-Witten transition, which means if I take one of these to the right, I get a D3 brane attached between the two. If I take one of these to the left, it ends up with a D3 attached. I still have my N there. So these two theories, they might differ in the UV, but they'll have the same IR physics. And if I have 2N hypermultiplets, it'll be just enough to account for the N rank of the gauge group. And then this will be, provided I drew these separated, but provided they're not Higgs or anything, this will just be regular branes, which could just be pulled off the NS5 brane. So it's very natural that the cutoff is at 2n. Okay, now the question obviously is, what's going to happen with these bad theories where the gauge group blows up? So again, in 4D, we have Seiberg-Witten theory, and the answer is known. So it's known for Seiberg-Witten theory, so 4D n equals 2. So this is worked out by Argyris, Flusser, and Seiberg, that if you have NF, well, I was calling it K, so K less than 2n, greater than n, then the baryonic root, where the baryonic branch intersects the Coulomb branch, has a dual description as SU k minus n plus some U1 to the 2n minus k. And so it's very natural to conjecture something like this happens in 3D as well. However, it's much harder to prove that this is what happens in 3D. What you can do is use the same arguments to match the, oh, and we also need plus some height, so plus some height in order to hit these. I think we need what you can do is match the Higgs branches of these two theories, the original one with SUN and the K, to this one, this Seiberg dual. But the full quantum dynamics and the metric and moduli space are unknown in the 3D case. So let me again derive this from the brain picture and then provide a little bit more evidence that this holds in the 3D case.
So what is wrong if you match and reduce these things?
Well, you have a bunch of new instantons emerging. So, and you don't have, okay, so part of the argument that you get this 2n minus k number of free U1s emerging is that the R symmetry group is broken by quantum effects to to a discrete subgroup. However, that statement is gone in 3D because there's no discrete breaking of the non-abelian R symmetry.
But there's this like procedure to kind of dimensionally reduce like 4D theories to 3D theories, and you add like these extra terms of the superpotentials.
Yeah.
Does that?
So you can dimensionally reduce, but then inferring inferring all the things you want to infer, I don't think it's trivial. These are things, yeah, I would like to think about them, but I don't know that it can be shown with the same level of rigor, as far as I know. So, well, the best evidence in this case, I think, comes from localization. But even with this dimensional reduction, you don't know the metric on the moduli space, except a few special cases, and you don't know
So
how
the electric theory is, I mean, it's just a SUN with a bunch of flavors, right?
Mm-hmm. Yes. So yeah, if dimensionally reducing worked, we could say, oh, here's the moduli space inside the Witten theory. Now, what is it in the dimensionally reduced case? And it turns out that you can't always do that. Although you can provide some overlap, some evidence, but it's not quite all there. Just because the appearance of lots of new instantons. Okay, so one like a sort of acute brain derivation of at least this part. Oh, and then sorry, K flavors charged into this. Still K flavors. You can do the following. So
Can I also, sorry.
yeah. Yes.
So those are the couple, or that there are superpotential terms that couple these theories together?
They're decoupled, I believe. Yeah. Well,
I don't know.
I'm pretty sure. I believe this is
On the magnet, on the other side?
the extra U1s you have?
Must be some interaction.
I believe, well,
Well, I mean, they're decoupled in the
low energy
in the
limit.
low energy
Yeah,
limit.
yeah,
There must be some irrelevant terms.
Sure.
That,
No, but in the low energy, those are just the couple factors.
Yeah.
You said, And so what goes wrong? Like, if you take the dual, I don't know. Maybe. So I believe that it is known, like, if you reduce,
Oh,
like,
if you
it's
reduce
single
this
factor.
theory, if you reduce this theory,
Yeah, both
already
theories.
decoupled, then sure. Then of course you would get this also decoupled U1 factors in 3D. But does that process of going to the solution and then flowing to 3D commute with flowing to 3D first and then looking for a solution?
I think the answer is yes, up to some instant factors that you have to write down.
Right, yeah. So yeah, that's a perfectly valid way of attacking the problem. And some work's been done on that. But, so, yeah. Okay. So here's a cute derivation. So again, I have N D3 branes and my K hypermultiplets formed by D5 branes. Now this will induce some brain bending. And since we're assuming we're in the regime where K is less than 2n, the branes want to bend and cross each other. So something like this will happen. Okay, now when the branes cross the D5 branes, they'll pull some D3 strings with them. So when this one crosses over here, it's going to pull some D3s that way. Likewise, this will pull some over here. So we'll have K new D3 stretched here. And then the D3s that were between these two NS5s oriented that way get flipped. The orientation's now that way. So we end up with K minus N, gauge factor, and then still the K hypermultiplets. Of course, what this misses are those free decoupled things. Now, from experience with N equals 2 and 4D, it's very tempting to think of them as living here somehow at the singularity. So this is where the strong coupling effects kick in, and this is where the enhance on radius is. So you can think about quantum effects Higgsing or Coulombing rather some D3s up to this point. So it's a nice picture, but we don't it's obviously not confirmed in the 3D case. So questions?
This picture kind of allows you to see the SUK minus n, and those extra U1s, not?
Well, no. So yeah, when the 2s5s cross, you can have singularities emerge, and no one knows how to derive this from kind of the brane dynamic pictures. So the brane dynamics works when a D5 cross NS5, and you can infer some things that way. But when 2s5s cross, I think we don't know the general rules because the singularity is too strong. However, at least in this case, I think we know that this is going to work. I mean, the dimensional reduction, negative dimensional reduction works in this case. There's various arguments, but the strongest one, I think, is this localization. So,
Can you just for myself, maybe naive, but those pictures, there are two terms of dimensions, so they are more like two cones coming together, or?
So these are all 5 branes. This is a 5 brane too. I just drawing it edge on.
So they have two planes with two conical things coming together.
Yeah, so I'm suppressing 2 of the dimensions. Here, for instance, yeah. So it's this should be thought of as actually a sphere, I think, because I'm just drawing sort of the radial dimension. So it's really a sphere across some S3, I guess, across some transistor dimension. Because this is representing all the points in the Coulomb branch where R takes some value. So well, I have the orientations up here. I erased them, but I can write it again. So yeah, we can talk later if you want.
R means the square root of like A3
Yeah,
cubed.
it's the SU2 invariant on the
So
Coulomb branch.
okay.
Yeah, so that's at a fixed value when we see this. Okay, so again, the localization argument is by far the strongest that this works in this case. And so Z S3 of this N comma K theory is equal to, as a function of various deformation parameters, Z3 of this K minus N comma K times Z of the hyper. Oh, and the U1 is dualized to a hyper in this case. So twisted hyper of U1.
This is in 4D or?
This is in 3D. So this is on an S3, just do a localization calculation. However, in this case, it's already very murky that this is actually proving the duality, because it's not, you can't actually go to the correct value. You would like to evaluate these where all the monopole operators have the correct IR R charges. So that's part of an input for doing a localization calculation, know the dimensions of all the operators. And we don't know the dimensions of the operators a priori. So you have to assume that the monopole operators have exactly dimension 1/2 in order for this to work, but then you don't even see that from this calculation. So it's a very murky statement, but I think that's as good as it gets for 3D.
So, and this would say that in 3D the dual is what? It's like SUN minus K minus.
Yeah, it's so the dual would be UK minus N with K flavors, and then a plus a so 2N minus K twisted hypermultiplet. So you could think of it as a pair of paramultiplets. So this has a 4 times 2N minus K dimensional modular spaces are all free and decoupled, and then this is now a good theory. So it has a weakly coupled description in the IR. Okay. So again, it's not as watertight as in 4D. Okay. So, any questions? So we can add one more layer to this story. Let me fix that.
So how do you get the extra U1?
These extra U1 factors?
Oh, going to go from SU to U.
Oh, sorry. Sorry. I mean, no, wait, no, okay.
I think
now
it's possible
you're
that you
getting me
can
confused. Now you're
better,
getting
yeah.
me confused.
No, I'm just asking how.
No, okay. I should have started with UNs. I think. My bad. That's sloppiness. So the duality applies with U's everywhere. So that was okay. Sorry about that. Okay. So one more layer. So it's very natural to generalize this UN gauge theory to a quiver theory, because that's what we get from the brain diagram, more or less. So, space. Okay, so when we draw this diagram, this was really compactified on a circle, so it's natural to see brains here as well. So this is a larger class of theories that, well, a slight generalization that's in the same class, I guess. So represented by some quiver N plus M. K hypermultiplets. Okay, and I want to put, for now, K hypermultiplets charged under the UN. Here I'll have N plus M. There's no hypermultiplets. And we can make the same classification to good, bad, and ugly in this case. And the criteria is the same. So I want number of flavors greater than equal to 2 number of colors, but now applied to both gauge groups. So this theory, for instance, has colors N plus M, and it has flavors 2N because there's going to be bifundamental hypermultiplets, those contribute flavors. So I have for the UN plus M, I have this criteria gives me number of flavors, which is 2N, minus 2 number of colors. N plus M has to be greater than equal to 0. And that just gives me that M is less than or equal to 0. So that's my first criteria. So obviously nothing wrong with M being less than 0. In fact, M being negative N just gives us back the theory we started with. And the second criteria, the same reasoning, is that M has to be greater than minus K over 2. So I have this window between minus K over 2 less than or equal to M. I haven't been careful about less than or equal to, but less than or equal to 0. Okay, so that's the window where both gauge groups are going to flow to weak coupling. So in this class of theories, I would like to know what are bad and good. You could approach this with various techniques, localization or dimensional reduction, but in keeping track of all these extra instanton operators. But keeping track of the instantons gets more and more complicated as the rank of gauge group goes up. There, in principle, is a classification. This Gallardo-Nekrasov-Moore paper, the wall crossing papers, in principle, they provide you all the data for the instantons, but it's kind of complicated. We're still going through that right now. So right now, I'm going to talk about the gravity dual. So we hope to learn a little bit about this theory from the gravity dual, but more importantly, I hope that as we learn more about the field theory, it'll teach us about singularities in the gravity theory. So right now, we've gotten this far. I've just outlined the problems, and I will try and create the bridge between this and gravity, and then see what we can learn from it. Okay, so. Okay, so okay, so first of all, I want to take the large in limit to have a good gravity description. Also, remind the picture again. This is periodically identified. Next, I want to scale. Yes, for LS. So I want to scale G-squared Yang-Mills the same way I would scale a Bev. So this is going to scale like some radius, some distance d over alpha prime. And these scalings demand that I collapse the branes together in this picture and go to near horizon geometry. But if I have to collapse this distance and this distance, I have to collapse the radius of the circle. So once the circle becomes substringy, I'm forced to go to a 2A description. So this scaling implies that we have to go to 2A. So next, 2A is complicated, it becomes simpler in M theory. So the strategy is 2B. We're forced to go to 2A. We go to M theory because it's simple. However, we're going to end up finding that the effective description was 2A after all. So we're forced to interpret things back in 2A. And this will provide us the criteria for when the theory is actually being well described or not. Okay, so following through that chain of dualities, I need to dualize the NS5s, I need to dualize the D3s, and also my D5s. So we have two NS5s. We're going to do T-dualize along this direction, which is, I'm taking to be the X6 direction parallel to the D3 branes that are stretched between these two. So these dualize to a top knot 2. Also, since I'm taking this circle to 0 size, I'll actually be forced to take the dual circle to infinity. The dual circle lives inside this top knot 2. And when I take that circle to infinity, I'm forced to go to an ALE2. So this is just an Iguchi-Hansen.
What is the T refer to?
It just refers to the fact that there are two singularities, or two centers. So it's like a top knot 2, and I've just taken the radius of the circle of top knot 2 to infinity. You could just say it's Iguchi-Hansen in this case, but we'll consider more general cases where the ALE has a different index. And then finally, lift to M theory, it's still just an ALE. It's still the same as Iguchi-Hansen in M theory. Now that we have the KD5 branes, those dualize to KD6 branes, and those in M theory are going to lift to top nut K. And then finally, this alpha prime goes to 0 limit, doesn't do anything to the top nut K, so the full dynamics of top nut K survive. The 1 doesn't drop out. So this is analogous to the statement that in field theory, the Higgs branch receives no quantum corrections, whereas the Coulomb branch receives quantum corrections. So all the information of the G-squared Yang-Mills shows up in the top nut K, and it shows up because I have that 1 still in the top nut K. Okay, and then the ansatz is the standard ansatz. The warp factor. We have a 3D metric, flat and Minkowski's metric. And then, since the orientations work out such that these two top nut, the top nut and the ALE are orthogonal, it's just d squared ALE plus d squared top nut k. Okay, so that part is actually pretty simple. And then we have to, of course, solve one equation for the warp factor. So we have the 8-dimensional Laplacian on the warp factor plus 1/2 Hodge dual, G4 self-dual, wedge G4 self-dual, and then plus some 2 pi some LP to the 6, which I'll do later shortly, times Q2 brain times the delta function. So in principle, we can distribute some into brains wherever we want in this 8-dimensional space. The ALE cross top nut. And this is 0. Okay, the only thing I haven't discussed is this 4 form. So we can put a self-dual 4 form on this ALE top nut space. As long as it's self-dual, presumably we'll preserve supersymmetry, and we will have a gravity dual of some n equals 4 3D Yang-Mills theory. So all the problem just boils down to constructing all these self-dual 4 forms in this space. Okay, so it sounds straightforward. However, there are some subtleties. So let's review a little bit the geometry of top nut, and then we'll construct this 4 form. The D3 branes? So they became D2 branes, they lived to M2 branes, and then the M2 branes are represented here by this Q2 brain. Although not exactly. This is not exactly the number of D3 branes. There's a shift I'll talk about later. Okay, so top nut.
I think another put like a finite number of two branes and get the theory of the two branes.
Sorry, what?
You could put a finite number of two branes if you want.
Yes.
Get the 3D theory of the two branes.
I think that's, yeah, isn't that what's happening?
Yes, yes, yes. These are approximately M2 branes. Like this term that I'm adding accounts for the presence of M2 branes and the gravity dual.
But you're not putting a very large number of them.
Oh, yeah, I mean, I'm assuming these numbers are all large.
I know what I was saying, you can put pro and two branes and study the theory of these two branes in this paragraph.
Yeah, actually, I mean, we'll do that. But we don't, yes, we do that at some stage. Okay, so review of top nut. So the metric on top nut. So that's some R11 squared. So this is going to be the asymptotic M theory radius, the circle radius. We have some scalar harmonic function, cube psi minus 1/2 omega. So this is some one form where psi parametrizes the circle. We have v dx squared. And then finally, this one form is defined as a solution to the Pogomoni equation, R11 dv. And last step we need is v is given by this. So I have a bunch of singularities, R11 with 2, x minus xj. So in pictures, I just wrote that because I need some of the notation later on. Okay, so in pictures we have a R3, and we're going to sprinkle some singularities on this R3 at the positions xj. And for each point on the R3, we have a circle fiber. And you can see from this, the radius of the circle fiber goes to 0 when we hit one of the xj. So if I draw the circle, it's bigger away from those singularities. And by drawing a line between the two singularities and looking at the circle fibered over it, we can find a compact cycle. So if I label these 1, 2, 3, 4, so on, I can form compact cycles by fibering the circle. So this defines the cohomology of top nut. One complication is that of top nut spaces or non-compact manifolds in general is that the cohomology is not necessarily dual to the homology. Okay, so in the homology, I have so J equals 1 to K, some 2 forms, and J. So although it looks trivial in cohomology, these aren't globally defined, so, but nevertheless, these lambda J have some explicit definition, which I won't write down. And the sum of the omega j's is in the what's called the non-compact cohomology. So it doesn't integrate to anything over the compact cycle, but nevertheless it's very important for understanding the charge quantization. Okay, now we can repeat the whole story for ALE. ALE2. And the only difference is that I'm going to drop this 1, and we can replace the R11 with any number we want. It's some scale. That scale will drop out of all of the field theory physics, so we can just give it a name L. So just replace that with something like this. V is equal to sum I equals 1 to 2 L over 2, I'll call it Y minus YI. And everything else is the same. And we could, of course, consider larger. If we have more gauge groups, this will be ALE 3, 4, and so on. Now, the big difference between the ALE and the top nut is that, again, I have these 2 forms, which are V of some pseudo 1 form. But now, the sum of these lambda i's is equal to d psi hat, which is, well, proportion to d psi hat, which is actually a closed form. It's actually globally defined. So the sum of the omega I hats is just 0. So we actually lost one of the forms in going from the top nut to the ALE. And this again has implications for charge quantization in these spaces, which I'll get to in a little bit. So that's the basic structure. We have a top nut with a bunch of 2 forms, and then we have an ALE with 1 fewer 2 form. And then we want to construct the general 4 form, so these are ingredients.
The top nut has K independent of 2 forms?
Yes. So it's K minus 1 in the compact cohomology, the K in the cohomology.
And just 1 for the ALE.
Right, yeah. Okay, so the most general free form and in theory we can write down with these ingredients. I'm going to set 2 pi LP equal 1. You can write down this. Some sum of one forms and two forms. Plus, we could also consider writing down pi bi hat, bi hat. Okay, and like you said, there's only one of these, but I'm just leaving the notation general for later. Wedge d psi, and then plus 1 over 2 pi bj omega j wedge d psi hat. Okay, so that's basically all we can do. Now, obviously, if I act with d on this or this, I get 0. So these are closed, and they don't affect the four-form self-dual field strength at all. So why would I include them at all? And one simple answer is that, well, although they're closed, this is a non-normalizable form, so it's not a pure gauge. So it actually affects the physics. However, as I'll show in a second, this one is going to affect the physics, and this one will not. So this one, I claim is irrelevant, but I'll show why in a second. Any questions?
Is it WJ is the same as W here in the terminal physics?
Sorry, what?
Oh, sorry.
Yes. So this is omega is for the top nut. It's using omega hat for the ALE, and this combination with the omegas from the top nut here, this is not going to matter for the physics. The other one will. So.
Were you asking whether it's the one that appears in the metric?
Yeah. Oh no. Okay. This omega was just defined by the Piccolomoni equation. Okay.
Is there a square on
Okay, so those omegas have nothing to do with these.
Yes.
close pieces.
Yeah, it's completely independent. Sorry. Bad notation.
Is the phi the angle?
Psi, yeah, psi is this angular coordinate. So it's psi, and we circle over each point. Okay. So, okay, again, these are non-normalizable forms, so in principle we should add them. Now, to see why one of those forms matters and the other doesn't, I have to go into the quantization rule a little bit. So here we have top nut, and then here we have draw the same thing with the ALE. We only have two singularities, so I have one cycle. So I can consider wrapping an M2 brane, the Euclidean M2 brane, on some 3 cycle. So I could wrap an M2 brane here on this 2 cycle. And I could also wrap it on a circle here. Okay. So this M2 brane, of course, will have some volume, and it's going to want to minimize that volume. So that M2 brane, it's stuck here, but it can go to one of these singularities if it wishes. So it'll likely fall to one of those singularities. And at these singularities, the M2 brane has 0 volume. So you would say it's a very powerful instanton, since it has 0 action, and it could mess up your path interval, strongly affect your path interval. Now, there's also a flux going through this M2 brane, and it gives rise to a phase. So at the point where the M2 brane has 0 action, the phase is IP, where phi is equal to, okay, so let me just define this first as a notation. Definition. J minus B hat I minus BJ. So at the point where the M2 brane hits one of these singularities and it becomes dangerous, the phase is Lij minus Lij. k minus 1. And then likewise, oh sorry, this is times. And then likewise, we could have wrapped this cycle and times a circle in the top nut, and we would have had the other phase similarly like this, ij minus L I minus 1. So in order to avoid having these instantons messing up your path integral with a bunch of random phases, you need, combining these two, you need the Lij's to be integral. So, okay, so that's going to be our quantization condition. Okay, so let me rewrite this with this quantization condition.
So you're saying the Lij's integral follows from saying phi and phi prime after the integral?
Yes.
What are those instantons?
Sorry, what?
What are those instantons? Is that
They're just M2 brains wrapping some cycle.
from the dual field theory point of view?
Oh, from the dual field theory point of view, well, there are two kinds of instantons. So you could think of them as D0 brains wrapping the S1. Well, that's using the 4D language. So yeah, I could give different perspectives, but these were the monopole instantons discovered by Polyakov in 3D gauge theories. So they have monopole charge, but
They have, so these are monopoles in three-dimensional field theory?
there's monopole instantons. There are things that have
the 3D.
yeah, they're just solutions of the. One way of thinking about it is in 3D, you could remove a point and then put some F2 flux through a surface around that point and define an operator insertion that way. So this is discussed in what is his name? The Willett, Yakov, and I can find the reference later. But yeah, they're just
Are those
natural things that appear in
the
3D.
usual BPS monopoles that you get in 3D, or no?
Yeah, so they have SUSY, and you can think of them as coming from 4D. If you take a monopole in 4D, and if it's going around the S1 after compactifying, you're left with a monopole instanton in 3D. So normal monopole in 4D is an instanton in 3D.
So you're saying that this M brain in the bulk, this is the ABS, this is the ABS configuration which is dual to this instantons in three-dimensional physics?
Yes.
And now what is this quantization condition, Lij belongs to Z? What is it?
Well, so from the gauge theory perspective, you've already inputted a lot of this by the time you say that the rank of the gauge group is integral, for instance. If you hadn't imposed appropriate quantization conditions for gravity, you'd be dual to something with a rank, or a gauge group SU 2.5. So this is partially just imposing things like that from the gravity perspective, that there's an integral number of hypermultiplets, not a fraction number of hypermultiplets. But it does also imply that everything is quantized as it should be. As far as I know, this includes all the quantizations in the field theory, in addition to the quantization condition you need to make the field theory make sense in SU n as an integral.
Do you find a rank if you have a gauge group with rank R, do you find an R independent solution to this quantization condition?
R independent? Sorry, what?
Like in 3D you expect to find kind of like R. If the rank of the gauge group is R, you expect to find R different instantons.
Oh, yes.
Or R independent instantons.
Yeah, that all works
Do you
out.
find that you do find R?
Yeah, so this set of instantons isn't necessarily one-to-one core. I mean, it includes those, but it might also include other ones. So counting these will overcount those. But yeah, those are contained in these. So I mean, the mapping between these instantons and whatnot has been worked out in detail, but not by me. So.
Just to saying that phi and phi prime are integrals seems to have a more general solution, which is the Lij are integers may be shifted by
Plus a constant, yes. Okay.
Does that not matter? Or?
It won't matter. Yes, you could do that. Okay. Let me say that. Let's just allow that for the time being, and we'll go away in a second. Okay. Okay. So let's write what we had before, but with this new notation. So Lij plus Bi hat plus Bj. And then lambda hat I, which is j, plus, so 1 over 2 pi, bj, omega j, with 2 psi hat, and then 1 over 2 pi, b hat I, hat. Okay, so now we're just going to use the fact from the ALE space that sum over lambda hat I equals minus 1 over 2 pi psi hat. Oh, yeah, okay, I was going to allow this as an extra term. And then you're going to see immediately that these terms, the bj's, are going to cancel against these bj's. And then what was I going to say about this gamma? So, okay, we thought about this some, and I forgot the full story, but part of it is this gamma, if it existed, if it was here, then it seems like it wouldn't affect anything, like doing probe analysis and whatnot. But also, if I did a integration by parts, then it would immediately go away because the sum of omega hat j is 0. Okay, so in terms of the field strength, it can't matter. And in the probe analysis, it doesn't matter. So if I had done integration by parts, write this over here, then the gamma would have dropped out, just due to this property. In this formulation, though,
Are you
so
trying
that's
to say?
telling us that it's only the differences of the L's that matters anyway.
yeah, it's the only difference of the L's that will matter in anything. Yeah, that is true. Yeah. For the ranks of the gauge ribs and everything.
You're trying to say that gamma is a gauge signature, that this way is defined out to gauge transformation, and gamma is a gauge transformation?
Yeah, it is, but it's not a. If I had included that as a gauge transformation, then it would not be a normalizable gauge transformation. But it just doesn't show up in any of the probe calculations that would be relevant for field theory. So I could do a probe analysis where I look at some brain, between these 2 and these 5s, and you won't detect gamma ever that way. So only the differences show up in those calculations, and it doesn't show up in the field strength. So I don't believe it has any physical relevance for gauge theory. Although that's the only argument I have at the moment. Yeah, I mean, normally it's weird from a certain perspective that you include these things in the first place. So we have to argue. You have to do a little bit of work to argue that these are even physical. To say that this is physical means there's some probe that measures these things, right? If there's no probe that can measure these values of these B's, then in a sense it's not physical. And in fact, there is no probe that will measure gamma because wrapping these brains on these cycles always gives you differences. So yeah, it doesn't seem to matter for anything. Okay, so we're left with, from what's going to matter for field theory, we're left with Lij and beta hat as our data. Oh, and you can do parameter matching for field theory too if this guy doesn't show up. So. I should note already with this quantization condition imposed on M theory, if we go down to type 2A, then you'll find that the Q4 page charges are quantized in units of 1/2. And in fact, if I had allowed for k hat separate gauge factors, like u in 1, u in k hat, then these would be quantized in units of 1 over k hat in general. And there would not be any necessary simple relationship between these page charges and the ranks of the gauge groups. It gets really muddled in this more complicated setup. But these anomalous shifts in the page charges have been deduced earlier, or some special cases have been deduced earlier on the basis of dualities. So what we're providing here is kind of a generalization of the rule for how page charges get shifted. Okay, that was an aside though. Okay, so I'm going to skip a lot of the analysis that goes into analyzing this theory and just review some of the results. So Hashimoto, Aharoni, Hirano, and Ouyang, they analyzed the case where all of the top node centers were at a single point, so the orbifold limit, and when all the mass terms and Fi terms are turned off. So it's a very simple case. And they found in that case that this Q2 brane is equal to n minus m squared over k. So that's what showed up looking like it was the number of M2 branes in my M3 description. But it's not actually the number of M2 branes. It's shifted by this weird negative amount. You can also relate this to the ADS radius. So Q2 brane related to the ADS4 radius, R6, ADS4, 64 K chi squared, LP to the 6. So it would appear that as long as Q2 brane is positive and we're in the scaling limit where all the charges are going to infinity, then the ADS radius is going to be very large. In fact, there's extra K over here to help it become even larger. So it would appear that that's a good theory under control with no significant curvature corrections. However, when Q2 brane is negative, then it looks like the ADS radius is imaginary or something, and it would look like this is something to do with an anti-brane. We have a negative brane charge. It also provides a negative brane tension as well as charge, because we're assuming this supersymmetric ansatz. So this looks like an anti-brane, and obviously something has to go wrong with our ansatz if this is going to be negative like this. This is like a repulsion singularity. Also note this criteria here that we get from supergravity has nothing to do with the good or bad criteria that we had before. This is effectively new, so, well, new as of this paper.
So, remind me what the good or bad criteria was for these quiver theories.
Okay, I'll draw it. Okay, so this is going to be m over k, the x coordinate, n over k, a y coordinate, and in terms of those coordinates, this just is k times y minus x squared. So it's just a parabola in these coordinates. So inside of this parabola, I have Q2 brane positive. The good and bad criteria was just that m over k is between 0 and minus 1/2. So there's some sliver here. So these are good. And these have no repulsion, these have repulsion. So one thing that's interesting is that there's a region here where we have a quote-unquote good theory that nevertheless sees a repulsion. So it's a naked repulsion. This is to be contrasted with the 4D theories where the repulsons are always shielded by being in the bad region to begin with. So there's always some kind of non-perturbative dynamics, in particular instanton corrections that will shield the repulsion. Here, these repulsons are not shielded by instantons. They're just, in a sense, naked. Now, since I said that this looks like anti-branes, I have a negative brain charge, and if I add anti-branes to a gravity background of branes, you think you'd break supersymmetry, and that's a very, very natural assumption. It's the assumption we started with. But if you think about it a little bit more, there's a stronger requirement for supersymmetry coming from field theory, namely that n is positive and n plus m is positive. And as long as that is true, there's no way to break supersymmetry with n equals 4. You can't dynamically generate a superpotential or anything. So as long as I can write down that Lagrangian, then the theory is supersymmetric. And so the gravity dual, if it exists, should be supersymmetric. So this thing that I'm writing here that...
Why is it?
Sorry, what?
N is... why is it?
Oh, n was the... Oh, so this was... These are all describing the theory.
S-U-N.
Yeah, UN times U n plus m. And I have k flavors charged under SUN.
So why is it that you can't break it? N equals what?
Well, because you can't generate a superpotential. Just like for n equals 2 and 40, there's no way to generate superpotential. There's just too much supersymmetry. Any superpotential would break a global symmetry. You can't. Instantons can't break a global symmetry. Or not abelian, sorry, not abelian. Okay, so the stronger criteria from gauge theory tells us that this is going to be the real criteria for Susi. So if I draw that here, I get something like this. So I just get a wedge. And all this will break Susi. Okay. So this is also very interesting because in this region here, for instance, we have gravity theories that by definition have a very large ADS4 radius. It's arbitrarily large in Planck units. And nevertheless, and there's no instanton corrections, and nevertheless, these are going to break supersymmetry somehow. So this is actually pretty weird, at least based upon our initial expectations, that this parabola is somehow mapped to Susi.
Let me get that. If this is satisfied, then there's no supersymmetry breaking. But how do you get the converse, that outside of this region, the supersymmetry will be broken?
Oh,
when
I mean, in this wedge, so I'm saying that in this, below this wedge and below here, Susi is broken. So that would correspond to having one of the ranks of the gauge groups actually being negative. And naively, that would be like actually having an anti-brane from the D3 perspective.
So, of course, it's not doesn't have a meaning per se as a field theory statement, you're saying, but from the brain, it gives you this intuition.
Right. Yeah, from the brain perspective, because I could write down a gravity theory with those charges.
Right.
There's nothing stopping me from taking a negative in the gravity description, but I know there's no possible field theory with n equals 4 Susi that satisfies that. And if there were a field theory, then I'd expect, sorry.
Is it obvious that you put a brain in anti-brain configuration, but the info, the effective 3D dynamics that you get still be described by n equals 4 theory? And you might not recognize what that theory is. You might not look at all like the description in terms of gauge theories.
Yeah. So actually, well, I wasn't quite saying that that's not true. and I'm actually going to say that what is true in a little bit. But what I'm saying is, at least if you flow to the IR and you focus on near the brains, if you, well, if I would say if I have a SUSY theory here, then it should correspond to some n equals 4 3D gauge theory. And there's no candidate, I guess.
Why should it correspond to a gauge of 3D gauge theory? My guess about the space of three-dimensional n equals 4 theories is there's a few special ones which are gauge theories, and then there's a whole mess. No. Anyway, that's good.
So okay, you're saying this might not correspond to a gauge theory, but
Something else. Some other.
yeah, I don't know. I could.
I'm just saying that
yeah.
we know very little
Yeah.
about the space of three-dimensional field theories. There are these those Westwoods and things like that.
Yeah. Well, at least I could, if I wanted to analyze this, I could start by putting in some brain probe in the UV away from all the nastiness and infer a field theory in the UV. And I would expect that it flows to something, but okay. So I don't have any other comments, but point taken. Okay. Okay, so putatively, I believe that SUSY is going to be broken below this wedge and below here. Now, I guess you could argue the same thing. You could try and work out all the spinner representations and whatnot. And I expect the same. Well, it's going to be impossible because once you're outside of this regime anyway, then you're not going to have a globally defined spinner, so you're not going to be able to apply the normal checks you would for supergravity to have a certain amount of SUSY.
Expand a little bit, add more details to that. What do you mean that it's not possible to understand whether supergravity is
So I'd want to look for some covariantly constant spinner in this background. So with 0. However, if I'm in this region, when I don't even understand the full geometry, the geometry is not, there's a repulsion. So particularly in this region, there's a naked repulsion singularity. So I have no way of defining the geometry over all space, at least at this level, at least without including lots of incident corrections. So I don't really know, there's no way to solve this question because the geometry is meaningless.
Do you mean you have a geometry with singular points? Or?
Not just singular, like singular radii, like whole regions are removed. So for example, in this kind of theory, there's a whole volume that's removed.
Right.
Due to, or the geometry becomes imaginary. So.
And that's presumably where identity brains sit, or something?
So yeah, I would say that in these theories there are anti-brains, but I'll get to that in a second. Okay, so one lesson from this though is that again, presuming that this line is SUSY breaking, is what we expect, is that a lot of these previous studies of anti-brains, for instance, they say let's start at the border of this parabola and perturb it a little bit. And we perturb it by adding an anti-brain and see how it back reacts. A lot of those studies might already be problematic because maybe you should have started here anyway. You should have started in a different place and added anti-brain on top of that. So this actually is a problem for our paper on anti-brains where we try to study this. Okay, so this is strange, but it's not as strange as you might think. There is one reason why this is happening. So like I said, we want to take all the number of brains to infinity. We're taking large n limit. However, the radius of the circle, the M-theory circle, is going to dependent upon this combination, if you evaluate the radius in this solution, it scales like this. And this goes to 0, of course, so we need to actually work in 2a. And in 2a, if you calculate the curvature in 2a, you're not calculating this curvature radius, you're calculating 2a curvature radius. And there's has a different scaling. So r squared 2a, it goes like alpha prime, root n over k. So you can see that when my y-coordinate here is of order 1, then I'm at large curvature from the 2a perspective, even though it's small curvature from the M theory perspective. And that's very weird, that it's the scale of curvature corrections changes when you go down to 2a. But nevertheless, that's what happens. So we need to work in 2a, and this region will in fact suffer from large curvature corrections. So we can't really say with confidence what is going to happen there. Incidentally, one should also worry about non-perturbative curvature corrections. So so in a series of recent papers, Itzhaki, Kudasov, and Gideon, they've been looking at MS5 branes. So you have some cigar geometry, and you have some winding modes here. Now, these winding modes, they can just slip off the tip of the cigar. So MS5. So you'd say, oh, they don't matter, they're not in the spectrum, but you should actually be defining your spectrum by looking at infinity very far away. So if you apply GSO to the spectrum far away from the branes, you find that indeed these winding modes should be allowed. But then once they come here, they become tachyonic. So if we allow for the condensation of these tachyonic winding modes, you find that there's going to be a non-perturbative alpha prime corrections in the vicinity of an NS5 brane. And what we're dealing with here is just the T-dual of NS5. So just as a side note, these kinds of worries might well apply to us as well. Okay, so now I want to talk more about this Q2 brane negative. And relation with anti-branes. Okay, so let me go back to this picture here. So we discussed this cyber duality, pseudo-cyber duality in the case with SUN, or UN, and K hypermultiplets. That generalizes to this case. Okay, and although the generalization in terms of the field theory language has not been developed yet, there's a very simple way to get a generalization of that duality working in gravity. So I said M ij is equal to Lij plus B hat I. So if I just send B hat I goes to B hat I plus 1, and Lij goes to Lij minus 1 for all I, then the Mij is unaffected. So this is actually going to not affect the field strength. And it turns out that this decouples in the IR. So doing this allows me to go from one gauge group, and this will represent a different gauge group, different set of charges, that should have the same IR physics. And this includes the cyber-like duality we discussed in the first place. So let's just look at what this sequence of dualities does in this case, so in terms of these coordinates, x equals m over k. This will be shifted by n to any n, and then y is equal to n over k is shifted to y plus 2n x plus n squared. So if I trust this duality, and again, we haven't evaluated how and when we can trust it, then we get some kind of sequence like this. So I start with some theory here, and then go down, 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 up. So it'll kind of form a parabola that asymptotes to this parabola. And likewise, if I pick a point here, it'll form a parabola that goes, dips below, and comes back up. Now, these cases have been worked out by localization. So just going from a bad theory to a good theory, we know that works, or at least there's good evidence. In this case, this would be a SUSY theory and a non-SUSY theory. So there's no evidence really, but it would be intriguing if something like that could be worked out, because it allows us to relate at least the IR of a SUSY breaking theory to the IR of a non-SUSY theory. And just looking at the numerology of the brain dynamics and the numerology coming from this sort of argument with large gauge transformation and decoupling at B, it seems to work, but that's kind of superficial evidence at this point. So this is one way, in a sense, that this theory with negative brain charge might be related to anti-brains, because if there is a relationship, then I can take anything with negative brain charge and actually relate it to the IR of a theory of anti-brains. That's still somewhat speculative, so I'm going to give a stronger argument now that's not so speculative. So if there is an anti-brain here, this does represent anti-brain and not just some weird effect of the nonlinear dynamics, then we should be able to pick apart this theory and see the anti-brain. And by pick it apart, I mean move the brains away that are kind of covering it. So we have, we derived this condition. We derived again Q2 brain equals n minus m squared over k. This was derived at the orbifold fixed point. So you can ask what happens if I start the orbifold fixed point and then turn on some VEBs for the hypermultiplets to give them some mass terms, or if I turn an Fi parameter and just generically deform away from the orbifold fixed point, we'll actually see an anti-brain. Okay, so to do this requires us to talk a little bit about how to deform these theories. So I introduced this notation Lij. Without much explanation, all I said was that it's something that's quantized. And you could ask, okay, what does this represent? Well, back in the language of Hanani-Witten diagrams, this is something to do with the ith NS5 brain and something to do with the jth D5 brain. So the only thing you could think of that connects those two is just the D3 brain connecting them. So now that I've set up notation, let me forget about having an ALE2. Let me just be general. I have a bunch of NS5 brains. I have a bunch of D5 brains. So I have k of these. If I have k hypermultiplets, I'll assume there's k hat of these just to make notation symmetric. And I'm going to be on a circle, so this is periodically identified. And I took a situation where I had a nice gauge theory with SUNs and k hypermultiplets. And all I did was I moved the D5 brains off to the right. You're always allowed to do this by Hanani-Witten transition. So if I started with a hypermultiplet here between these two, I could have moved it off to the right at the price of having a brain attached between the two. So the most general configuration I can imagine, once I write it this way, is that these NS5s are attached to these D3s, by some arbitrary set of windings, and they could go around the circle. And that is basically all that can happen in supergravity in the limit, well, in the case where I'm turning on Fi and mass parameters. Or in this case, I'm shifting these brains in the transverse directions. So to see that this is all that can happen, note that if, for instance, a brain were to stretch between the 2n5 brains, with an Fi turned on, it would break SUSY. And what I've written down is putatively a supersymmetric ansatz with self-dual flux. So one expects generically nothing like that can happen. And so we're left with this as the generic configuration with Fi mass parameters turned on. How am I in time?
You're a little bit over it.
Oh!
Yeah.
Okay, sorry. Let me just get to the punchline then. Yeah, Blackboard talks take a lot more time. Okay, so we have this Lij's. You can do a whole bunch of checks that the Lij's represent this. So if I have connection here, and this is the third brain, and this is the second one, I have Lij, sorry, L3, 2 equals 1, for instance. Lij can be larger than 1. You just need to wrap around the circle multiple times so you can pick Lij to whatever numbers you want. Now, let's draw, again, this diagram. So my good theories in this region, my SUSY breaking condition, and if I also require that there are no anti-brains, and now I know what anti-brain, now I'm talking about like the discretely quantized thing, not this Q2 brain. If I require there's no brains, no anti-brains when I separate things, then you end up with a region like this. So it's kind of some kind of polyotope that very closely approximates this parabola. So inside this polyotope, this is number of M2 brains greater than or equal to 0. And anything outside of this will actually be left with an anti-brain if you try to pick it apart. So we see that fortunately we missed this region. That's good, because that would have been very weird if we put everything apart and there's nothing to break SUSY. So this gives me further evidence actually that we found the right SUSY condition. Is that this lines up perfectly inside here. What's more interesting though, I think, is that out here in this region, there's effectively an anti-brain, but sitting at the bottom of this, well, sitting somewhere in this geometry. So if I deform everything, I'm stuck with an actual anti-brain, and I'd break SUSY. And that's what you expect from field theory. You turn on all these Fi math parameters in these theories, and you break SUSY. Here you can do it. You can save SUSY, but by only by going to these discrete vacua. Here, I would break SUSY completely. But what's interesting from the gravitational perspective of this whole anti-brain debate is, if I started at the orbifold fixed point, and I just say I start here at the orbifold fixed point, and I drop it in anti-brain, such that the charges take me outside the parabola. Well, I know what happens. The anti-brain just drops to the bottom of the parabola, and it just sits there, and it's a SUSY theory. So by studying instant time corrections, again, in principle, it's doable. We can actually describe a gravity dual of an anti-brain theory. It doesn't annihilate, it doesn't go away. It's still there, and you can see it by deforming the orbifold. So it provides at least some kind of example where the anti-brains might make sense in a gravitational dual description. So there's other things I was going to say, but I think I'm over time. So I guess that's it.
those anti-brains, what do they mean from the future point of view? What kind of future will you have if you have anti-brains in the ball?
It's, well, if it's not at the orbifold fixed point, then the anti-brain just means I'm in a configuration of the field theory that's broken supersymmetry. So I've excited the field theory to some higher energy.
So this is like a metastable state?
Well, in this case, it's not metastable. So in 4 dimensions, Klebanov-Strassler situation, you have these metastable. Some people think you have metastable vacua. It's a big debate. In this case, there's no metastable situation; it just drops to the bottom. But we have more control over these theories because there's actually a SUSY vacua that it goes to, and it doesn't annihilate. There's no brain flux annihilation.
So okay, so if it's not a metastable state, if it actually drops to the vacuum, but this vacuum is not supersymmetric. That's what you're saying, right?
I know. I believe these are supersymmetric.
Okay, so if you start with under the brains and then they flow into supersymmetric vacuum. On the bulk side, you would not see the brains anymore, right? They will annihilate.
Well, okay. So it's maybe a terminology what they mean by annihilate. So if they annihilate, so the annihilation is a process where a bunch of energies released and whatnot. So that's the perspective of Klebanov-Strassler.
You started with some state above vacuum, then flow into the vacuum. Of course, some energy will.
Yeah, that much is true. But that's like a ball rolling down a hill versus a ball rolling down a hill and then kind of exploding. I think that the main difference is here. In this case, there's a trace of the anti-brain left. Like I would see it if I deformed the theory. Whereas in the Klebanov-Strassler case, the anti-brain is supposed to annihilate, and then there's no way to recover it in a sense. There's no deformation you could do to see the anti-brain.
I'm not sure I understand the statement. In the Klebanov-Strassler case, you start with a non-supersymmetric state, which is not vacuum, and if you tunnel into vacuum, that's a supersymmetric vacuum. Then forget about whatever you started with. You just end up in a supersymmetric vacuum.
Yeah.
So I try to understand what is the solution in your case.
That much I think is the same. I guess the only distinction is that in some sense you would, in this case, see the anti-brain if you turned on Fi mass parameters. That the trace of the anti-brain is there because it makes the Fi mass parameters rigid. So that's all I mean, is that there's some residue of it.
Residue in the sense that the vacuum is supersymmetric, but you would not end up in this vacuum. I'm not sure.
It's unique, like it's isolated.
What is the residue of anti-brain? I'm not sure. So
That it.
if I find myself in a supersymmetric vacuum, do you want to say that there is something which can tell me how I ended up there?
Well, no, but I'm saying one way of thinking about the fact that it's an isolated vacua is that you have an anti-brain there pulling in all the other brains and keeping them from moving apart. It's maybe an intuitive picture, but I don't mean anything more than that, I guess. If you deform the parameters, you'd be left with an anti-brain. Like there'd be a physical anti-brain left there if I turned on the mass in Fi, whereas in the Klebanov-Strassler case, I don't know what I could do to recover the anti-brain in the end. So in that sense, I think they're a little different, but maybe it's just terminology. I don't know.
Is that starting from the gravity the initial point?
Sorry, is this in the in theory? Sorry. Sorry, what? I just didn't catch it. Sorry. Can you say it again? I just didn't hear it.
Okay.
Well, we're using M theory just to get the solution, but we're thinking of it as a two-way solution. Type 2A, yeah. Type 2A is the correct description. It's the effective description.
So I said that there are certain parameters which I can view, and in that case, anti-brains did not annihilate, that would stay in the gravity background forever.
Mm-hmm.
That would be stable.
Yeah.
could you explain what would be the dual field theory state in that case? So if I understand it correctly, there is a way you can choose certain parameters. You will have gravity backgrounds with entity branes, and that is a stable configuration, right?
So if I was in this theory, for instance, and I turned on phi and mass parameters, then you just break supersymmetry. So in the field theory, it's just no supersymmetry.
So what is
It would
what
be
kind
a
of,
non-supersymmetric vacuum.
that would be a vacuum of non-supersymmetric field theory.
Yeah.
Your
That's-
Lagrangian
that's what
itself
this-
is not supersymmetric.
Right.
I think
Okay.
that's what he's saying.
Okay, so then you have non-supersymmetric field theory. In that theory, you have vacuum that is described by entity branes in the bulk.
Yeah.
And then if you restore supersymmetry at the level of the Lagrangian, those entity branes annihilate.
Then there's the unique supersymmetric
And
vacuum.
okay, then I guess the only thing which I don't understand is this story with remember and then the brains or whatever remnants of entity brains.
No, I don't think that's what he meant. He meant that if I do deform the theory,
Right.
the same object would appear to be, the same object in a different theory would appear to be stable. That's what. Am I right?
Yeah, the same bulk applies to different field theories. I think that's what is the conclusion, right?
Yeah.
Well, same bulk configuration. Sorry.
Same bulk configuration.
Join.
Yeah, yes, yeah.
So if we change bulk a little bit, we can end up in different field theories with different stories, with no supersymmetry.
Yeah. So yeah, I agree on that.
Okay, let's go. So